So we're going to start talking about where we see organic chemistry used today. And these are just a few relevant examples of careers where people actively use organic chemistry. So nurses, optometrists, in med school, a vet, organic chemistry, biology, zoology, agriculture. Really what I'm getting at here is that a quote captured by Albert Einstein, I think really says this poignantly. It's not so very important for a person to learn facts. You don't need a college education because you can learn facts from books. But the value of a college education is the training of the mind to think. And so that's really our focus today, is to train our minds to think and learn how to solve problems more efficiently. So I promised an unscientific survey of shortcuts. These are some ways that are pretty common for us to draw molecules. The long version is what you see on the left. The shortcut is what's shown on the right. Notice it's really clear what you're omitting. So whether that's charges or lone pairs, whether that's using a line drawing instead of showing all of the hydrogen bonds, if you're omitting the CH bonds, or if you're just using an abbreviation. I don't mind you using these abbreviations or shortcuts as long as you understand what you're leaving out. So it's a great resource if you're working on saving time. So I want you to think about what you know so far in terms of general chemistry, and I want you to draw or write pentane 3 different ways. We're going to move on, so if you want a moment to just pause, go ahead and hit pause, and then when you're ready to go, come back to us. Here are some of the ways that we can draw pentane. You'll note that they're all different. What are some of the things that they have in common? Here are some of the ways that they're different. We talked about the benefits and limitations of using models last class, and it's worth it to think about the way that we represent a molecule and the type of information that conveys to us. As a recap, let's look back at Lewis structures and polarity. So why do we even bother learning about Lewis structures? Why is electronegativity important, or formal charge? We can derive dipoles based on our understanding of how we draw a Lewis structure, what electronegativity is of the atoms, and then what the formal charge is that we can calculate. And if we know where dipoles are, then we can show sites of reactivity. For example, experimental data shows that the positively charged acid, the H+, will react at the negative atom bearing the electrons. So in this case, that's the oxygen, whereas the negatively charged hydroxide, that's the example on the right of the screen, will react at the atom bearing the partial positive charge. In this case, the carbon with the blue delta plus. So these are 2 great examples of how, if we understand Lewis structures, electronegativity, and formal charge, then we're able to start to predict where a molecule is going to react. For light bulb number 2, I want you to practice drawing Lewis structures. But in this case, I've given you the answer. I want you to choose one of these molecules and describe the process that you would use for drawing this Lewis structure. So if you're not yet comfortable drawing Lewis structures, this is a great way to get some additional practice in. It's also really helpful to think about your process. How do you know what to draw? How do you know where to put bonds? Or how do you know where to put electrons? These shouldn't be structures that you memorize. Rather, they should be structures that you make sense of and then are able to train your mind to think to learn how to draw them. So again, if you need a little bit more time, press pause. We're going to keep moving. But this is a great chance for you to get practice in if you need it. We're going to talk about valence shell electron pair repulsion theory. And what's shown in this chart is the arrangement in space of bonds and lone pairs. So for example, E is our central atom. X are atoms that are bound to that central atom. The 2 dots are lone pairs. And you can actually see that the arrangement in space is such that it optimizes separation. Atoms want to be as far apart from each other as possible on a molecule. And that goes back to that idea of attraction versus repulsion. All molecules are going to optimize distance. They're kind of like siblings. You sit on your side of the car, I'll sit on my side of the car. But it's useful to be able to think about how we might use these sheets. They're not always the same. So when we're thinking about VSEPR, and molecular geometry, it's usually important for us to think of, right, the number of unbonded electron pairs, so that's the number of lone pairs, and then the number of electrons that we see in the valence level of our central atom. And that's going to tell us something about what type of shape it's going to take. You're going to notice that there's something true in terms of these formulas. You can start to observe patterns. Value for you in terms of patterns is thinking about what do I already know and how can I use that. So ask yourself, which column is easier to fill in first? Think about strategy. What is it that you need to know? What is it that you already know? If the letters change, can you still solve or assign molecular geometry? If you know the total number of bonds and the total number of unbonded electrons, can you get to the same place? These are great questions to ask when you're practicing these topics. We're going to spend a part of today talking about resonance, which is a way to describe molecules and the ions for which no single Lewis structure provides an accurate representation. So here are 3 Lewis structures for the carbonate ion. Which of the 3 is correct? Can you draw the movement of electrons to go from structure A to structure B? Again, if you need a little bit of time, this is a great opportunity to press pause. So Linus Pauling in the 1930s recognized that many molecules or ions are best described by writing 2 or more Lewis structures. These individual Lewis structures are called contributing structures. You can connect individual contributing structures by a double-headed, also known as a resonance arrow. The molecule or ion then that results is actually a hybrid of all of the various contributing structures. So in reality, carbonate exists in form A and form B and form C. We use a curved arrow because this is the symbol that shows the redistribution of valence electrons. So if we're using curved arrows, there's only 2 types of electron distribution. We can distribute electrons from a bond to an atom or from an atom to a bond. And we can push those electrons by using curved arrows, and that's going to be a really important skill for you to practice in organic chemistry. You want to practice it often. So here's a double-headed resonance arrow example. I've shown the hybrid of the 2 structures on the right, and I've also shown an example of a carbocation and the resonance that it can form. So notice you can form resonance for negative charges or for positive charges. We're moving electrons as long as, right, I have a place to move the electron, I can use a resonance arrow. It's really important here to state that resonance structures are not in equilibrium with each other. They're not isomers. Isomers actually have a different arrangement of both atoms and electrons. Resonance forms differ only in the arrangement of electrons. So when we think about isomers, we're thinking different compound, same molecular formula, 2 different kinds that you're familiar with, constitutional isomers and stereoisomers. Resonance is a hypothetical arrangement of electrons. We don't actually have the ability to see electrons well. So what we recognize is that likely it's a hybrid. It's something that lives between the resonances. So here's a curved arrow. This is one way to show the movement of electrons. So we can take the electrons from the tail and move them to the head. We can go from a bond to a lone pair, from a lone pair to a bond, from a bond to a bond, but we can't go from lone pair to lone pair. So for resonance structures, we can only use curved arrows to form or break pi bonds. We never actually break single bonds. So here's some examples of the legal moves of resonance. So pi to lone pair to pi bonds, and then an illegal move, which is lone pair to lone pair. So take a moment, think about nitrous oxide. N2O, laughing gas, is a colorless, non-toxic, tasteless, odorless gas. Because it is soluble in vegetable oils, fats, it's used as a propellant in whipped cream. How many valence electrons are present in nitrous oxide? Can you write 2 equivalent contributing structures for this molecule where the connectivity is N bonded to N bonded to O. Be certain to show your formal charges if there are any that are present, and then think about why the following is not an acceptable contributing structure. Again, if you need to, press pause. Take as much time as you need to think about solving this problem. So if we think about how many valence electrons we see, right, in nitrogen, right, each nitrogen is going to have 5, and oxygen is going to have 6. So our total would be 5 plus 5 plus 6, so we should have 16. If we write the two equivalent contributing structures, we're going to start out by trying to distribute our bonds first, and then we're going to add in, right, lone pairs if necessary in order to make sense of or account for all 16 valence electrons. Now there's a rule that says that anything below neon cannot have an expanded octet. So the reason why we can't draw the structure in C is because nitrogen, whose atomic number is less than 10, cannot have an expanded octet. When you think about resonance, we're really thinking about the movement of electrons, but we could also think about the movement of charges. So, for example, experimental observation is that bond lengths in the allyl cation are going to be identical, and the positive charge is distributed equally. That means that the resonance hybrid of the allyl cation is comprised of both of the possible resonance structures. So, how do we evaluate resonance forms? Take a look at the structures that you see here. The first rule of evaluating resonance forms is that it has to be the form with the least number of charges. That's going to be the most stable. And that's what contributes the most to the resonance hybrid. Rule number 2 is, it's the principle of greater electronegativity. So we always break a pi bond so that we put the electrons on the more electronegative atom. An alternative way, or a more general formulation of saying this, is negative charges are ideally placed on the atoms best able to stabilize them. So draw 3 resonance structures for this molecule. And again, take a pause if you need to. Based on electronegativity, then, we're going to, for light bulb number 6, we're going to determine the second best resonance form for each of these molecules. So what are the alternate resonance forms that you can draw? Choose one and determine which is the second best form. The last thing we're going to talk about today are the shapes of orbitals. So when we think about orbitals, we're talking about, again, the distribution of electrons, but we're talking about whether or not they're distributed in a sphere, for example, an s orbital. Notice the more electrons you have, the larger an orbital becomes. A p orbital, this is where I have 2 lobes that kind of look like balloons that are arranged in a straight line. So when I'm thinking about a covalent bond, that's going to form when some portion of my atomic orbital of one atom overlaps with some portion of an atomic orbital of another atom. So for example, when I form the covalent bond HH, there's an overlap of the 2 1s orbitals of each hydrogen. So take a moment and draw an s and a p orbital. Where do you think they would overlap? So if we think about constructing methane CH bonds, we might start with an overlap of a hydrogen 1s orbital and one of carbon's valence shell atomic orbitals. So in this case, carbon's blue, right, not colored, and yellow, and they're all perpendicular to each other. The 2 CH bonds formed from carbon, you would think would be perpendicular, but we actually know that methane's actual HCH bonds and their angles are 109.5, not 90 degrees. So using carbon's p orbitals doesn't give the correct bond angles. Notice, this is going to be a resounding theme, where quite frequently experimental results overturn theories. So even scientists sometimes are wrong. In fact, I would argue for any change to happen in science, you have to be wrong about something. So when we study 3 types of hybrid atomic orbitals, we're looking at sp3, sp2, and sp. Hybrid simply means the combination of an s and 3 p's, or an s and 2 p's, or an s and 1 p. The overlap of hybrid orbitals can form two types of bonds, depending on the geometry of the overlap. Sigma bonds are direct overlap, pi bonds are formed by parallel overlap. So take a moment and state the type of orbital hybridization that's used with each steric number. So the steric number of a molecule is the number of atoms bonded to the central atom of a molecule plus the number of lone pairs on the central atom. What do you think happens to non-hybridized orbitals? Again, if you need a moment, take a pause. Each sp3 hybrid orbital has two lobes of unequal size. The four sp3 hybrid orbitals are directed towards the corner of a regular tetrahedron at angles of 109.5. If I take a look at two p orbitals, I can see the overlap to form a pi bond. This is what I see with ethene in A. Another representation of that is in B. C is another representation showing that pi bond. D is the way that those electrons actually look in space. If I look at formaldehyde, I can see that it's not just for carbon-carbon, it can be for carbon-oxygen, or even for triple bonds like acetylene. So here's the pattern that I'm looking for. If I have four groups bonded to carbon, then that orbital hybridization is sp3, and the predicted angle that I would expect to see is 109.5. If I have three groups bonded to carbon, then that's sp2, and the predicted angle is 120. And if I have only two groups bonded to carbon, then that's an orbital hybridization sp, where I have predicted bond angles of 180. It's useful to take a moment and try and capture what we know about hybrid orbitals, especially if it's a concept that we're not familiar with. This is an example of a concept map. We start with what we know, and the bright yellow, the hybrid orbital model, assumes that atomic orbitals are in the valence shells of atoms and that they combine to form hybrid orbitals, which hybrids of a given type are going to be geometrically equivalent. They can accommodate bonding electron pairs or non-bonding electron pairs. We use the hybrid orbital model to help predict molecular shape. It's also most useful when the central atom is the representative element. It's less useful for things like the transition metal coordination complexes, metals in general, or quantitative calculations. But we can use hybrids of a given type to determine SNP or SN2Ps or SN3Ps to determine the hybrid orbitals. These are actually connected to the wave functions that describe one or more atomic orbitals. And if we wanted to think about the molecular geometry, if we look at non-bonding electron pairs, whenever I have lone pairs present, they're going to reduce the symmetry of molecular shape and cause it to adjust. So for example, an sp3 tetrahedral hybrid geometry with one lone pair becomes pyramidal, with two lone pairs becomes bent. I want you to take a moment and see if you can spot the common mistakes in organic chemistry. Can you figure out where the mistakes are? Again, take a pause if you need. So for the top block, it's drawing a pentavalent carbon or other second row elements. For the second block, it's not including formal charge. For the third block, it's showing Lewis structures that fail to properly represent the intended structure. And for the last block, it's not recognizing identical structures. We're going to have a little bit more practice with this shortly. In fact, we're going to do a lot of practice with this next class. But it's important to recognize that the way we represent molecules, going all the way back to the beginning of lecture, is something that actually helps us understand how they react. And so it's useful if we can recognize when molecules are identical or when they're different. The last task that we're going to talk about is functional groups. So functional groups are atoms or groups of atoms within a molecule that show a characteristic set of physical or chemical properties. It's important for us to know functional groups for three reasons. We divide organic compounds into classes based on functional group. They're also the sites of characteristic chemical reactions, and they're the basis for naming organic compounds. So I want you to take a moment and see if you can brainstorm. How many functional groups are there with oxygen? How many functional groups are there with nitrogen? How many functional groups are there with carbonyls? And again, if you need to, take a pause. So an alcohol is a compound that contains a hydroxyl group bonded to a tetrahedral carbon. An amine is a compound that contains an amino group, a nitrogen atom bonded to 1, 2, or 3 carbon atoms. We classify amines as primary, secondary, or tertiary according to the number of carbon atoms bonded directly to the nitrogen atom. Carbonyl groups of aldehydes and ketones, that's a C double bond oxygen. The carboxyl group of carboxylic acids, that's a C double bond oxygen and a single bond to oxygen. I want you to think about amino acid functional groups. At this point, you should be adept at drawing 2 amino acids. What functional groups are present on those molecules? Take a look at glycine and alanine. You should see that there's an amine functional group, and there's also a carboxylic acid functional group. Next time, we're going to be talking about acids and bases. Thanks. We'll see you soon. Bye.